Good morning. Welcome to e-learning. I am P. Saktivel, Assistant Professor, Department of EEE, Thandai Periyar Government Institute of Technology, Vellore. Today's topic, switching regulators. A switching regulator is a circuit that uses a power switch, an inductor and a diode to transfer energy from input to output. Types of switching regulators: buck regulator, boost regulator, buck boost regulator and cuck regulator. Buck regulator. In a buck regulator, the average output voltage is less than the input voltage. Boost regulator. In a boost regulator, the average output voltage is greater than the input voltage. Buck boost regulator. A buck boost regulator provides an average output voltage which may be less than or greater than the input voltage. This diagram shows the power circuit of buck converter. It consists of source voltage Vs, chopper switch S, diode D, inductor L, capacitor C and resistance R. This buck converter, also called step down DC to DC converter. This buck converter consists of DC input voltage source Vs, controlled switch S, diode D, filter inductor L, filter capacitor C and load resistance R. Let us assume continuous conduction mode. Continuous conduction mode means the inductor current is never zero. When the switch is on, the current flows through the inductor L, load R and partial current flows through the capacitor and the inductor stores the energy. This diagram shows when the switch is on. It is the equivalent circuit when the switch is on. Here the main switch is act as a closed circuit. So now the current flows through the inductor and load R and the source and partial current flows through the switch. It is the power circuit diagram when the switch is open. Here it acts as an open switch. Now the inductor releases the stored energy. Now the current flows through the inductor, load R, diode D and partial current flows through the capacitor C. This diagram shows the output voltage and output current waveforms, and also this waveform shows the capacitor current and the source current. Now the output equation. The voltage across the inductor capital L is equal to E suffix L is given by L into di by dt. When T on, that is during the on period, the inductor current rises linearly from I1 to I2 at the time of T1. So the value of dI is I2 minus I1, the value of dt is T1. And the voltage across the inductor is equal to Vs minus Va. So Vs minus Va equal to L into dI. dI is I2 minus I1 by dt. dt is T1. From this, T1 equal to delta I, where delta I equal to I2 minus I1 into L divided by Vs minus Va. Consider this as equation number 1. When the switch is off, that is T off, inductor current falls linearly from I2 to I1 at the time of T2. That is here delta I equal to minus of I2 minus I1 and delta T equal to T2. So the first equation, that is Vs minus Va, now the source voltage is 0. So minus Va equal to minus L into delta I by T2. From this, T2 equal to delta I L by Va. Consider this is equation number 2. Equating the value of delta I in equation 1 and 2, we are getting delta I equal to Vs minus Va into T1 by T equal to Va into T2 by L. Substituting T1 equal to Kt and T2 equal to 1 minus K into T, then the average output voltage Va equal to K into Vs. Assuming a lossless circuit, that is Vs equal to Vs Is equal to Va Ia equal to K into Vs Ia. That is, we proved that Va equal to KVS by substituting Va equal to KVS into Ia. Then the average input current is given by Is equal to K into Ia. See here, Va equal to K into Vs, but in terms of current, Is equal to K into Ia. The switching period T can be expressed as T is equal to 1 by F equal to T1 plus T2 equal to delta I L Vs divided by Va into Vs minus Va. Now substituting the value of T1 and T2 in the above equation and finding delta I, the delta I can be given as delta I equal to Va into Vs minus Va by FL Vs by equation 3, and one more equation 4 can be written for delta I. Delta I equal to Vs into K into 1 minus K by F into L. So here we are substituting the values in terms of K. The inductor current IL using KCL equal to IL equal to IC plus I naught. Assume load ripple current delta I is very small and negligible, therefore delta IL equal to delta IC. The average capacitor current which flows into for T1 by 2 plus T2 by 2 equal to T2 by 2 is IC equal to delta I by 4. The capacitor voltage is expressed as V suffix C equal to 1 by C integration IC into dt plus the initial voltage across the capacitor. Peak to peak ripple voltage of the capacitor is delta Vc, and delta Vc equal to V suffix C minus V suffix C at the time of 0. That is given by 1 by C integration 0 to T by 2, and IC value is given by delta I by 4 into dt. It is written as delta I into T, capital T by 8C, and delta Vc equal to delta I by, that is T equal to 1 by F. So 8FC, it is given as equation number 5. Now substituting the value of delta I from equation 3 or 4 in equation 5, we are getting delta Vc equal to Vs into K into 1 minus K divided by 8LCF square. That is in terms of duty ratio. Thank you.